Yes, it is permissible to reduce the minimum required cover depth for an underground duct bank or raceway that is concrete encased, as dictated by the National Electrical Code, specifically Section 300.5 Dun and 2. According to Section 300.5 Dun, the general requirement for underground installations mandates a minimum cover depth of 24 inches. However, an exception exists in Section 300.5 D2 for underground service conductors installed in a raceway. In this case, the minimum cover depth is reduced to 18 inches. It is important to note that this particular section does not explicitly state that the raceway must be encased in concrete for this reduction to apply. Similarly, Section 300.5 D3 addresses underground service conductors or cables installed in a duct. Here, the minimum cover depth is also specified as 18 inches, and again, there is no explicit mention that the duct needs to be concrete encased to qualify for this depth. However, 300.5D exception provides clarification. It distinctly states that the minimum cover depth can be further reduced to no less than 6 inches for underground service conductors when installed in concrete encased ducts or raceways. Therefore, it can be concluded that the standard minimum cover depth of 24 inches can indeed be reduced under specific circumstances. Firstly, for underground service conductors installed in a concrete encased raceway, the minimum cover depth can be reduced to 18 inches. Secondly, for underground service conductors or cables installed in a concrete encased duct, the minimum cover depth can also be reduced to 18 inches. The underlying rationale for allowing this reduction in cover depth when concrete encasement is employed lies in the enhanced protection that concrete provides to the underground installation. The concrete encasement acts as a physical barrier, significantly reducing the likelihood of damage to the conductors or cables from external factors such as excavation activities, heavy traffic, or other potential mechanical stresses. In essence, the concrete encasement offers an added layer of security, justifying the reduced cover depth requirement. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines that govern the safe installation of electrical wiring and equipment in the United States. It is developed and maintained by the National Fire Protection Association, or NFPA, and is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. Adherence to the NEC is crucial for ensuring the safety of people and property from electrical hazards. The NEC addresses a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, bonding, equipment installation, and special occupancies. It provides specific requirements for various types of electrical installations, taking into account factors such as voltage levels, environmental conditions, and the intended use of the electrical system. The NEC is not a law itself, but it is widely adopted by state and local jurisdictions as the basis for their electrical codes. This means that compliance with the NEC is often legally required for electrical installations. Electrical inspectors use the NEC to evaluate electrical work and ensure that it meets the minimum safety standards. The NEC is organized into chapters, articles, and sections, making it easy to find specific information on a particular topic. It also includes numerous tables, figures, and examples to help clarify the requirements. It is important for anyone involved in electrical work to have a thorough understanding of the NEC and to stay up to date with the latest revisions. The sections mentioned, such as 300.5 Dun, 300.5 D2, 300.5 D3 and 300.5 D exception are very important. 300.5 pertains to underground installations. The requirements outlined in this section are designed to minimize the risk of damage to underground cables and conductors, which can lead to electrical hazards such as shock, fire, and power outages. Firstly, Section 300.5 of the NEC specifies the general requirements for underground installations. It mandates that all underground cables and conductors must be protected from physical damage by being installed in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, or cables specifically listed for direct burial. Secondly, Section 300.5b addresses the burial depth requirements for underground cables and conductors. The minimum burial depth varies depending on the voltage of the cable or conductor. the type of wiring method used, and the location of the installation. Thirdly, Section 300.5c covers the requirements for underground splices and taps. It states that all underground splices and taps must be made in approved enclosures that are suitable for direct burial. These enclosures must be designed to protect the splices and taps from moisture, corrosion, and physical damage. Fourthly, Section 300.5d addresses the specific requirements for underground service conductors. Service conductors are the cables that run from the utility company's transformer to the building's service equipment. This section specifies the minimum burial depth for underground service conductors, which is typically deeper than the burial depth for other types of underground cables. Finally, Section 300.5e covers the requirements for underground wiring beneath buildings. It states that underground wiring is prohibited beneath buildings unless it is installed in rigid metal conduit or intermediate metal conduit. This requirement is intended to prevent damage to the wiring from building settlement or other structural issues. Concrete encasement is a method of protecting underground electrical conduits and cables by surrounding them with concrete. This technique provides several benefits, including increased physical protection, improved heat dissipation, and enhanced resistance to corrosion. Firstly, physical protection. Concrete encasement provides a robust barrier against physical damage from external sources such as excavation equipment, heavy traffic, and soil movement. The concrete effectively shields the conduits and cables from impact, compression, and abrasion, reducing the risk of damage that could lead to electrical hazards or service interruptions. Secondly, heat dissipation. Concrete has a relatively high thermal conductivity, which means it can effectively transfer heat away from the conduits and cables. This is particularly important for high current conductors, which can generate significant amounts of heat during operation. By dissipating heat more efficiently, concrete encasement helps to prevent overheating and extend the lifespan of the electrical system. Thirdly, corrosion resistance. Concrete is naturally alkaline, which helps to neutralize acids in the surrounding soil. This can significantly reduce the rate of corrosion of metal conduits and cables, especially in environments with high levels of soil acidity or salinity. Concrete encasement also provides a physical barrier that prevents direct contact between the metal and the soil, further reducing the risk of corrosion. The depth of the concrete encasement is an important factor to consider. Generally, the encasement should be thick enough to provide adequate physical protection and heat dissipation. The specific thickness requirements may vary depending on the type of conduits and cables being used, the soil conditions, and the expected traffic load. It is important to consult with a qualified engineer to determine the appropriate concrete encasement depth for a particular application. The type of concrete used for encasement is also important. The concrete should be strong, durable, and resistant to cracking and spalling. It should also be compatible with the materials used for the conduits and cables. Portland cement concrete is a common choice for concrete encasement, but other types of concrete may be used depending on the specific requirements of the project. The installation of concrete encasement should be performed by qualified personnel who are familiar with the relevant codes and standards. The conduits and cables should be properly supported and aligned before the concrete is poured. The concrete should be thoroughly vibrated to ensure that it fills all voids and encapsulates the conduits and cables completely. The concrete should also be properly cured to ensure that it achieves its full strength and durability. In summary, concrete encasement is a valuable technique for protecting underground electrical conduits and cables. It provides increased physical protection, improved heat dissipation, and enhanced resistance to corrosion. By using concrete encasement, electrical systems can be made more reliable, durable, and safe. Underground service conductors are the electrical conductors that run from the utility company's distribution system to the service equipment of a building or structure. These conductors are responsible for delivering electrical power from the utility grid to the customer's premises. Due to their critical role in the electrical system, underground service conductors must be installed and maintained in accordance with strict safety standards and regulations. Firstly, conductor size. The size of the underground service conductors must be sufficient to carry the maximum electrical load of the building or structure. The conductor size is determined by the ampacity, which is the maximum amount of current that the conductor can safely carry without overheating. The ampacity of a conductor is affected by factors such as the conductor material, the insulation type, and the ambient temperature. Secondly, insulation. Underground service conductors must be insulated to prevent electrical shock and short circuits. The insulation must be suitable for direct burial and must be resistant to moisture, abrasion, and chemicals. Common insulation materials for underground service conductors include cross-linked polyethylene, or XLPE, and ethylene propylene rubber, or APA. Thirdly, protection. Underground service conductors must be protected from physical damage. This can be achieved by installing the conductors in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, or cable specifically listed for direct burial. The conduit or cable must be buried at a sufficient depth to protect it from excavation equipment, heavy traffic, and soil movement. Fourthly, splices and terminations. Underground service conductors must be spliced and terminated in approved enclosures that are suitable for direct burial. The enclosures must be designed to protect the splices and terminations from moisture, corrosion, and physical damage. The splices and terminations must be made using approved connectors and methods. Fifthly, grounding and bonding. Underground service conductors must be properly grounded and bonded to ensure electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to trip circuit breakers or fuses and prevent electrical shock. Bonding connects all metal parts of the electrical system together to create a low impedance path for fault current. Sixthly, marking and identification. Underground service conductors must be clearly marked and identified to prevent accidental contact during excavation. The conductors can be marked with color tape, labels, or other suitable means. The location of the underground service conductors should also be documented and made available to contractors and utility workers. Seventhly, inspection and testing. Underground service conductors should be inspected and tested regularly to ensure that they are in good condition and are operating safely. Inspection should include a visual examination of the conductors, conduits, and enclosures. The testing should include insulation resistance tests and ground impedance tests. The National Electrical Code, or NEC, provides detailed requirements for the installation and maintenance of underground service conductors. It is essential for electricians and contractors to be familiar with these requirements to ensure the safety and reliability of the electrical system. Understanding the specific requirements outlined in Section 300.5d and its exception is critical for safe electrical installations.